At the Research Institutes of Sweden, the printed electronics arena, we've developed a new technique that combines screen printing and a synthesis technique that improves the organic printed materials and also their performances in printed electronic applications. Improving the materials, customization of devices and manufacturing process will allow better performing devices to be achieved, which may even broaden the field of printed electronics and its applications. We've combined screen printing with a technique called Vapor Phase Polymerization, or VPP for short. Now VPP uses an oxidant or a precursor that's deposited on a substrate and then is exposed to a chemical unit. After some time, the chemical unit and the oxidant combine together to create longer chain units, and these are called polymers. Specific polymers that have alternating single and double bonds can carry electrical charge, and these are called conjugated or conductive polymers. Up until now, VPP has usually been constrained to spin coating and small scale, since spin coating is quite problematic to upscale. Combining VPP with screen printing not only allows us to upscale the process, but also to create patterns of 100 micron resolution.
Patterning becomes important when it should be incorporated into functional components. In one of our latest manuscripts, we show that this combination of technologies can be used to create all printed organic electrochemical transistors, OECTs in short. One of the crucial parts in an OECT is a semiconducting or even conducting film called the channel, which is usually made out of a conjugated polymer. This channel is in direct contact with the source and drain electrodes. The electrolyte, which is printed between the channel and gate, allows for operation at low voltages, about 1 volt. This low voltage operation, together with the organic materials, result in an interesting device that can be used in many applications, for example in logic circuits and within bioelectronics. These devices were created by carefully aligning and printing several functional layers on top of one another, and the resulting device outperforms the commercially available materials that are used in similar devices.
We then took the technology one step further by extending the technique into other conductive polymers in order to illustrate the adaptability of the method and incorporate these conductive polymers into all printed electrochromic displays. These multi-layered thin display devices are fabricated by printing multiple screen printed layers which are aligned, and then an external voltage is applied in order to change the color of the conductive polymers. In our study, we present 3 different conducting polymers in all these all-printed electrochromic displays. Our first polymer is P dot, which switches between dark blue and light blue. A derivative of P dot is currently used in commercially available displays that are commonly integrated in low-cost sensors and other technologies. The other electrochromic polymers that we used are polypyrrole, which exhibits a bright yellow to grey blue state, and polythiophene, which switches between bright red and a blue color. With sheet-based screen printing being employed, these materials are made at large scale and in various patterns for displays. The main restriction, though, on the upscaling of the research is now the size of the chamber needed for the exposure to the chemical units. The extension of this technique to other conducting polymers opens up the possibility of other low-cost multicolor thin film displays and other functional components which previously have been impossible due to the lack of these impressive materials and their deposition at large scale.